Welcome, everybody. This is the 15th of October, 2024. This is the Open Research Institute's meetup for field programmable gate array work and also for SDR work and remote labs work. And so what we do at this meeting is we talk about what we've done over the past bit of time, usually a week, what we have planned for the next week's worth of work, if we need any resources from ORI, and if we have any roadblocks. So what I'll do is I'll go ahead and kick it off here. I'm going to talk about a roadblock that we have right now with Opulent Voice, which is that the tracking loops for the demodulator do not appear to be working as expected. Now, the interesting thing about this problem is that they're working in simulation according to Matthew. They're not working on the hardware. And so what I have here is just a little bit of drawings of the first exploration through the HDL. What I've been doing is working from the processor side. So this is the application layer, ordering around the registers and trying to get things to work. And we haven't really gotten there yet. We've seen some occasional good behavior, but mostly not. So this is the view of the Pi controller, or would be the proportional integral controller. That's a fundamental part. It's buried deep in the MSK block. This is an entity. So these are all the ports, the inputs and outputs, the generics, the constants, and the signals. It's written in VHDL. And so pretty straightforward. We understand what we got here. And our original blame was resting on this part of the design. So when you back out a little bit and you look at all of the things that are done outside of the processes, so you have processes within a module in VHDL, logical processes that are concurrent. These are the things that are outside of those processes. And what's always running is a calculation of the sum and the calculation of the saturation values on the accumulator sum. So we have an error, LPF error that's coming in, turned into a sign, re-signed, added to the accumulator. We present that as the sum. We check it and see if it's positive or negative limits have been reached. And in the lower right-hand corner, you can see that there's a drawing of what we consider to be the limits. And the next part is to go into the different processes. And so we've started that to kind of dig through and to see if what we are getting at the application layer is truly reflected in the code. So we think that coming at it from both sides, so to speak, will eventually defeat this particular problem that we're experiencing. All right, so I'm going to turn off the share. That's just to showing you how we explore through the code and how these drawings will eventually be part of the documentation for this particular block. This PI controller block is within the Costas loop block. That is within the MSK demodulator block. That block is within the MSK top block. And somewhere along the way, the loops are misbehaving. All right, that's what I've got from the past couple of days. And we also have a lot of things to report from the digital update for microwave. That was our workshop that we did from the 2nd of October to the 10th in Vancouver, British Columbia. What we did there was also work on Opulent Voice. And I think the biggest success, at least for me, was seeing the signal go from too wide of a bandwidth, unintentionally wide, down to exactly what it was supposed to look like. And all of the side lobes and the main lobe, everything looking really good. And so that was an iterative process, back and forth with people testing it and people working on it. Another big tranche of work was investigating iterative receiver designs. So that was sort of more of a research rather than development. So we did both R&D when we were in Vancouver. All right, so I'm going to hand it off to Paul, who who has some things to present. He's also been deeply involved with all of this work on Opulent Voice, and the floor is yours.
Okay, got to click the right things. Thank you. We had all sorts of interesting adventures trying to get the code to behave and to understand how it was behaving while we were there. I've got a little picture of what that waveform you described looks like that might be worth presenting if I can share.
Yes, go ahead.
Um, let's see. I want to share a partial window this time. Can I do that? Um, if only I knew how. All right, let's do it a different way. Um, well, okay. It's not going to work apparently.
You should be able to share through Zoom. It's set up for multiple people to share.
Yeah, I'm not having trouble with that. I'm having trouble operating the local client.
Oh, okay. Well, we'll wait. No worries.
I've opened a window. It's supposed to be just that so I could share the window, and now it's just blank. All right, never mind. I'll mess with that while we're doing something else and try to bring it in later. And what I
Okay.
do want to present is a little adventure we had debugging a build. Um, we had been trying to do builds in different places on Choco Cat and on local computers, and from different people doing it with instructions from various sources. And we've been having some trouble with a local build on Michelle's computer. But then Matthew's computer started having a problem with the build too, in nearly exactly the same place. Um, he was building on Choco Cat, which had always worked up till then. So I'm going to try again to share the screen with just some error messages showing so you can see what I'm talking about. You see that?
Yes.
Okay. So these are excerpts from the chat on Slack that we had about it. So Matthew reports, my build is failing now too. And here's the error message trimmed down to its very fundamentals. It says at the very bottom there, you can see uh, bad file descriptor and this mysterious number 6538. Um, that didn't make any sense to us. It looks like it's related to this copy command. Okay, so Matthew's theory was maybe there's a system issue because bad file descriptor is something that really shouldn't happen very much. Um, it suggests that you've tried to do something with an open file that you can't do with an open file, or maybe two people are using it, or it's a very confusing error message. And still, what the heck is a 6538? I thought it might be a process ID. Um, he says it looks like it's related to the copy command, and I couldn't figure out how a copy command could cause a bad file descriptor error. Thought it might be a process ID. He says, no, I don't think so, because it's always the same. So process IDs are rotating all around on Unix systems. So it's never going to be the same twice unless you're extremely lucky or unlucky. So there are other possible ways that a bad file descriptor error could come about. I thought maybe there was something wrong with the system. There was a file that was locked open somehow. Usually a reboot will fix this problem. So I suggested a reboot, got everybody to agree that rebooting wouldn't cause them problems, and rebooted the system. And what do you know? It had exactly the same error. Um, so that theory was out the window. Um, Matthew said that he would have to look into the make file and try to understand what was going on. But he had already tried this make-n and make-d. These are ways to get make to cough up some debug information while it's running. And make-d is supposed to pretty much tell you everything that's going on. But he didn't get anything useful out of that. So I had to figure out what make-n and make-d were. So I went to the man page and looked it up. And what I saw there was that there's also this one called dash dash trace, which actually outputs each command before make runs it. So I suggested that. I suggest we try that. And Matthew ran it. And here's the output he got. It's almost the same. But look at this. That's one line, really. Let me stretch it out so you can see that it's just one line. That is where that's the command it's actually running when the error comes up. It's an echo command. And it's echoing, trying to make a string here and then redirect it into this file, the versions file that gets incorporated in the build. And then it gets the bad file descriptor. But look, this bad file descriptor number is right here in the, I don't know if you can see my pointer or not, is in the redirect command right before that angle bracket. Now, that's revealing. That's what's going on here, really. Because if you put a number right before the angle bracket on a Unix command line, it means to take that number as a file descriptor and redirect into that. You may have seen this as a figure 2 and then an angle bracket. And if you have a figure 2 and then an angle bracket, that always means redirect standard error, because standard error is always file descriptor 2. But it turns out you can put any number there. And if you put a number that's completely made up, like 6538, it's going to be a bad file descriptor. Why hadn't this been a problem before? Well, if you go back and look, where did that number come from? It's the first 4 characters of the commit hash, because that's what we're trying to put into the version string to identify the particular build. And most times, those 4 characters of the commit hash are going to have one or more letters, A through F, because it's a hex number. And the last few builds that we'd had letters in them. This one's all digits, so it looks like a number to the command line. And because it's right up against that angle bracket, it's treated as part of the redirection. It's trying to redirect the echo command into file descriptor 6538. And it's going to completely ignore the path to where we thought we were redirecting to. And it's because 6538 isn't really a file that's open, it's a bad file descriptor. Kaboom. And the solution is to go and put a space after the 6538 before the angle bracket, so that the angle bracket causes redirection is not associated with that number. And that fix worked. One character added to the make file where it's just white space, shouldn't matter, but in this case it did. And I thought that was really kind of deep and fun that we figured it out. So that's my story, and I'm sticking to it.
Right on. Thank you. I think that that ties the record for the smallest pull request for a open source project, which was a colon to RF or sorry, yeah, RFSoC for GNU Radio, because they left out a colon in a list update for the make file for RF So one character. Sometimes that's all that matters.
And a space at that. Yeah.
And it's a space. It's not even yeah, it's essentially a blank space. All right. So yeah, it looks like it's going to work. The issue was filed. The pull request is sitting there waiting for Everest to review it, and yeah, now we're back in business and able to build things. So and the whole point of having the hash in there, it's really kind of nice, because when you log into the Pluto, um, you see that as part of the splash screen, and it immediately lets you know what you're working with, so that you can tell that you actually did successfully update the firmware on the Pluto, which version you're working with. It's nice, but we did not anticipate that all digits would cause this trouble. So live and learn. All right, so let's let Aaron have the floor and tell us what's been going on and plans for the future, and if anything's needed.
Sure. Yeah. How's it going? Can you guys hear me?
Yes, you sound great.
Okay, all right. So I've been working on the Spectrum viewer still, and I actually want to demonstrate it to you guys today.
Oh, outstanding. Yeah, please go ahead.
You see my screen?
Yes.
Okay. So this is a diagram of what I have running. Starting on the top left here is the Pluto SDR itself, and in the light blue is the what's running on the FPGA. So we have the analog to digital converter taking in 20 megasamples per second signal in, and it's feeding into what I we call a triggered sampler. So it's basically allowing the samples to come in, but only when I want it to get triggered. It's going to take 196 samples and feed that into the windowер, which then gets fed into the FFT. So the FFT size is 496. And then from there, this is still in the OpenCPI domain. And then in OpenCPI, there's ACI stands for Application Control Interface. And this allows us to interface to other applications. And it's running an MQTT publisher that publishes the results from the FFT, the fast Fourier transform that's running on the FPGA, into the MQTT broker. And this is using Everest, the Pluto SDR version that already has the MQTT broker running in the firmware. And then separately on another, right now it's on my VM. There's an MQTT client that takes those results and computes the power, the log power of it, so that we can display it. So I want to take all the credit here because Jay Ledet, and this is the GitHub where I found this open source way of displaying the Spectrum viewer in a browser using WebSockets. And his implementation uses the EDIS, UHD, and GNU Radio to display it. So I modify it to use the OpenCPI. And basically, I just have a Pluto SDR with an antenna attached to it over USB. And the problem with the USB interface is that it's such a small pipe. And using libIO or GQRX, you can only get 2 to 3 megasamples per second. And if we just want to see what's out there on the spectrum, by using this implementation, we can see up to 20. And I even tested up to, for this implementation, the maximum is 30.72 megasamples per second, because we're using the CMOS one port interface of the 809361. And kind of the whole reason I was doing this, because I was looking online for another geostationary satellite, the QO100, and they had this nice spectrum viewer showing what is being received. This is on the ground station side, but the idea is to have this on the satellite itself to see what transmitters are transmitting on the system itself. So now this is this is the spectrum plot that implemented. So this is in a web browser using HTML5 canvas. On the top here, this is live right now with the antenna. To the left here is the 70 centimeter ham band. And this is the commercial band because there's a lot of traffic in it, and you can see it working. You get about 90 seconds of waterfall here. And right now it's running at four frames per second. You can increase that by changing how fast the trigger sampler works. And I've tested it up to 30 frames per second, and it comes out really fast. Yeah, so what I plan on doing in the future, I do want to get this prototype into a more completed state. And what that means is include documentation, publishing the pre-built artifacts so that anyone can just plop it onto their Pluto and run this. And that includes a continuous integration pipeline. But also, I do want to change the implementation a little bit such that you don't require, this doesn't run on a separate machine. So I have a diagram here of what that would look like. So a new FPGA component that would actually compute the log power, the log base 10 and the power on the FPGA, and then moving away from MQTT because that's not necessary, and embed a WebSocket server directly into the OpenCPI application control interface such that you run the application and then all you have to do is go to 192.168.2.1, which is the IP address of the Pluto, and just pull up a browser to it. And then once that's complete, some of my thoughts, and I've started investigating this future would be to handle everything on the FPGA such that we end up feeding the DVB-S2 modulator that will be running on the satellite in the future. But some other things that can be done is, and I've started to investigate, is since now we have this um, web browser kind of interface, we can take advantage of things from the web browsers, such that like accessing the microphone and the speaker. So we can have a push to talk here and implement opulent voice. And so there's something called a media source, and I was looking in, and actually already supports Opus, the Opus codec, and we can utilize, so take samples from the microphone, have them encoded using the Opus codec, and you can set it up to do the exact the scheme that we're using, and then send that over to the processing system to frame it using the RTSP and the UDP and then the IP layers as well into the opulent voice framing, and then send it out to the transmitter, the MSK transmitter that we're currently building. And then from here, you can also do the opposite, which using the speaker, decode the Opus coded voice and have it play over the speakers. And then you can use Bluetooth headsets and any type of headsets that are already interfaced with that we're using now for this conference, things like that. Some other things, interesting tidbits that I've been able to pull from this example is at 4 frames per second, it utilizes up 168 kilobytes per second of bandwidth. It's 1.38 megabits. So thinking of the end goal of having this on the downlink side, we have about 10 megabits worth of. So we can adjust that so we don't use that as much, but we can get a view of what transmitters that is being seen by the satellite. So yep. So that's my work on the spectrum viewer as pertains to FPGA and opulent voice.
Thank you. That's outstanding. And it fills in a whole lot of things that we don't have yet. I think we know in principle that we're very committed to, like, HTML5 is really a great way to access things, and it makes it very accessible, very portable, very useful. And starting to see it actually happen is just so fantastic. So thank you. This is wonderful. And leveraging the onboard microphone and speaker for the Pluto has been in block diagrams for a while, and plowing through the protocol and deploying the prototypes that we have. These have been very standalone sort of prototypes. Like we know that they work. We know with like Opus, but seeing the connection here, and seeing that there's a much better path than we thought is very inspiring and very positive.
That's another thing I accomplished this last week. I was able to compile the C++ version of Opulent Voice and play around it with a little bit and encode some bit streams with it to see how it works and see what the output files sizes, and like each 40 millisecond chunk is around like 1.3 kilobytes, so which is really good. So trying to tie these in together is what I'm trying to do.
Fantastic. Yeah, thank you. I think, Paul, do you have any comments or questions or?
No, just that I think that's fantastic. Doing it through the web browser that way will save us an infinite amount of work trying to get it to work on different platforms. It's the right answer.
Yeah, for sure. Now, Aaron, is there anything that you need or that you don't have that would be nice, or anything that do you think we should be paying more attention to or doing over the next week?
No, not right now. like I said, I kind of my plans are trying to get this in a complete state, and then maybe jump on board the MSK stuff to get that squared away. That's something I want. I with time plan on doing this if time allows. But thanks.
Oh, of course. Yeah, that's what we're here for. Cool. Okay, let's see. What else have we been up to? Paul, what have I missed?
I don't know, but I've got that spectrum display ready to share if you like.
Yeah, very good. You have the floor.
Okay, let's see if I can do it. This is actually a movie. This is what it looks like. I assume you're seeing it. I want to play just so you can see it wiggle. Um, it's about a little bit more than 80 kilohertz wide for the main lobe and nice and round. And the first side lobe here is a 20 dB down. You can see it here, 55, minus 55 for the top of the main lobe and about minus 75 for the top of the first lobe. And then it curves down the way it's supposed to. So that is what the waveform, the MSK waveform, is supposed to look like. And now it does. And that's great. This is, by the way, this is a SDR++ running on a Mac using a HackRF as the interface. So this is much more accessible to a home lab than our Regal Spectrum Analyzer is, which we have shown numerous screenshots of before. But this is uh, just as good, except when it's not.
Yeah, thank you. That looks like it's supposed to. We were working with and debugging the MSK HDL with a much wider signal. So it was accidentally wider because of the selection of the two frequency words in code. I think. So it was a um, after we backed up and dug through and figured it out and got the frequency words that specify the F1 and F2 sorted out, it came right back into focus and looked good. Yeah, it's really exciting to see because it looks pretty much like it looks in textbooks. Um, so speaking of textbooks, we've used a lot of them and gone through a lot of papers. What we're doing for the modulator and demodulator is very heavily based on Hardgott and Massey's work, which dates back many decades. So minimum shift keying is relatively new modulation, new in the sense of that people were working on this in the 1980s, and it's kind of not gotten as much attention and exploration in the open source community as it deserves. It's got a lot of advantages. So we've talked about these advantages in the past, but just to kind of summarize, it's extremely spectrally efficient and is very well behaved when it comes to filtering. So there are claims in the textbooks and in the documents that we've been relying upon that you really don't need a transmit filter for a modulation scheme like this. We probably will still do some filtering. But if you're familiar with GMSK or Gaussian minimum shift keying, then you know that it's a go-to for putting lots of different signals into a crowded band. So as an amateur open source project, we don't have the same sorts of constraints. For example, we don't have to extract lots of money from subscribers for using our system. So we can afford to kind of like back off from the GMSK and do MSK and fully explore the advantages and disadvantages of that. And so that's kind of where we're at here. So it's the sort of the overall thrust of this. It's a big improvement over the 4-area FSK that all of the other digital amateur VHF, UHF voice protocols use. So we're starting to see some of the on the air benefits of it. And this will be um, a, a really good design, specified, fully open sourced, and documented, where people can learn about minimum shift keying and really kind of explore that modulation. So it will stand out in the community. It's it will be a significant contribution to both open source and amateur radio and digital radio. So thank you to everybody that's been helping here. Matthew couldn't join us today, but he's very active on Slack. We look forward to seeing him next week. And Ken, who's working on the receiver side, on the satellite side, has had a few steps forward this past week and is looking forward to sharing that. He, unfortunately, due to work, he's not able to join us today. And we have lots of other folks that are pitching in and helping out and supporting us as a community of open source folks. So I just want to say thank you to everybody that's making this very ambitious work possible. When we talk about this particular communication system, it's will live as a point-to-point terrestrial mode, maybe an HT on its own. And we're making it as easy as possible to use on off-the-shelf SDRs, so that you should be able to get a Pluto, program it, and then use all of these neat functions to do great, very high quality voice data integrated without a separate clunky mode. And also to have some authentication and authorization built into the protocol. This will also be the uplink protocol for a larger a satellite system. So that's the future, and we're getting closer every week. So thank you, everybody. Any last comments or questions before we close? All right, so we wrapped up the digital update for microwave series of workshops. It went well enough to where I think we should do it again next year. So DUM is in the books, and perhaps we can call the next one DUMII or dummy, and we can get dumb together again, about a year from now. It's focused on the workshops are, actually like hashing through the code. So it's sort of like a hack fest with emphasis on over the air demonstrations. So stay tuned for that. Let's see, what's the next? Do we have another event coming up? We do. It's a regulatory event. We will be hosting a virtual workshop about the 219 megahertz band and a proposal for rulemaking to the FCC. So we are talking about writing up a proposal to renovate the rules for this haunted band in amateur radio. There are no current users of the band. It's people are not operating on it, but 219 is a really neat band, and use it or lose it. So we are addressing some of the issues with the spectrum management decisions that were made many decades ago that have led to a total stagnation on this band. It's allocated to us as secondary users, and we're fixed digital stations, but relatively the high throughput. So that's what we're looking for is to draft a set of rules to propose to the FCC to allow it to be much easier for us to use and to increase activity on the band. A really great place to explore and use digital radio, preferably open source. That's coming up on October 25th. It'll be this meeting time. So on October 25th, you'll show up and we will be talking lots and lots of regulatory stuff about the 219 megahertz band. So I hope all of you will join us there too, and weigh in on how you think the current rules should be changed in order to make it easier for us to use the band for open source digital radio work. All right, everybody. I'll see you next week and on Slack. And thank you so much for all of the time and the attention. And it's because of your work that we're able to do ambitious things. So very deeply appreciated. And see you soon.